Hi, I'm Gary, and I want to show you how I use Cloudy. So today we're going to talk about how to extract lines from the Cloudy predictions. In many cases, people will run a model or range of parameters and want to look at how lines change or match an observed spectrum. So we follow classical atomic spectroscopy as much as possible. So in that spectroscopy, you would identify an emission line or absorption line by a spectrum. O3 is one example, it makes the strong lines in the optical spectrum. So that would, in textbooks, it may be written as Roman numeral 3. We use O3. And then you give the line wavelength. So this table shows a series of oxygen 3 lines. So the first and third are the strong mid-IR lines, 88, 52 micron, and then the bottom two are the strong optical lines, 5007, 49, 59. They're so familiar, they've got them memorized. These wavelengths have a letter at the end showing the designation because we work across the entire spectrum. A is angstroms, M is microns, C would be centimeters. There's a nuisance here is that you have to specify the line wavelength to the precision we have shown here. The problem is that some spectra are very complex. The worst, perhaps, is molecular hydrogen. The famous 2.121 micron line that people talk about in the near IR has actually three or four molecular hydrogen lines that are very nearly that same wavelength. So you have to specify wavelength at high precision since we follow the tradition of finding the line by the wavelength and the spectrum here. There's a save line labels report option that we talked about in the previous video, and it generates a list of all the lines in Cloudy and the format that looks like this. So this is an entire line, and I've broken it in two halves so we can see them with a bigger font. So these are, again, the oxygen 3 lines. This is an index of the line in Cloudy's internal emission line stack. So this is the spectrum, and then these are the lines. The rest of this line, if you look at these line labels, tells you where the line came from. And in this case, the hash mark means that the rest of it is a comment. This index is the level index in the stack of states that Cloudy uses to figure out a spectrum. So index equals 1, index equals 3 would be the first state or the third state in that stack of states. The E low is the low energy in wave numbers and a different way of identifying the low state. And then stout here tells you that we're using the stout database. And then the rest of the line is the designation of the quantum level using LS coupling notation. In general, this field here will have information about the entry that you're looking at. In this case, it's a database line, so it has a lot of database information. This is a small chunk of the optical lines from the M16 simulation going into the PDR. So we see a lot of things you recognize. So here's O3, 4959. Here's helium-1. See a lot of blend. We see lots of kind of weird stuff. Some of it makes sense, like helium-1, nitrogen-1, some does not. This is the wavelength again, all in angstroms here. The next column gives the log of the luminosity of the line from the prediction. We'll come back and talk about that a lot. So this is in ergs per second as a log. So this is the what we would call the absolute intensity because this is the amount of power going into the universe. This is the relative intensity, and it's conventional in spectroscopy to give a line ratio of the line you're looking at divided by a common reference line. In the optical, it's frequently H beta. In mid-IR, it may be the carbon-2 line, but this tells you that 5007 is 5.5 times stronger than your reference line. This is the same part of the same model, and near IR. So here we've gotten into a part, we've included Cloudy's complete molecular hydrogen model, so we see lots of H2 lines. So this is around the 2.121 micron line. At low resolution, many of these H2 lines mix together and you just see one line. We want to help observers. I use Cloudy to interpret observations. So we create line blends, BLND. We'll come back and talk about it in a few slides, which add together other lines that are in the neighborhood so you can simulate the spectrum that you would actually see in a telescope. So this blend is the sum of other lines that would be appearing as a single line in a telescope. Others have different things. If you go back to that report, and if you were to look up case B, this line, it would tell you exactly what that line is. So the way you find a line in Cloudy is go to the Save Line Labels output and find it. And so this is some weird labels here. If you wonder what O3BN 507 is, well, this explains it. So this is defined in this continuum band sub dat file, which is in the data directory. So you can figure out what that is. In the cases we've done so far, the M16 models, I've included these three commands. In its default state, Cloudy will report the line spectrum in an order that makes sense to a programmer, but not to a spectroscopist. So if you want the lines to be in a sensible order, at least to a human, you might want to include these three commands. So print lines column means you get one big long column of output. Print line sort wavelength means they're sorted from the shortest to the longest wavelength. Print lines faint allows you to prevent the code from printing or reporting lines that are far too faint to be seen. So it makes the output more useful. Well, is that complicated enough? Here comes one more complication. It's in atomic spectroscopy from the 19th and 20th century. The convention was set up that spectroscopists use vacuum wavelengths for the hard ultraviolet vacuum for wavelengths less than 2,000 angstroms, and air for wavelengths bigger than 2,000 angstroms. It had to do with how they built an laboratory apparatus. For short wavelengths, the mean free path of photons in the atmosphere is very short, so they had to build the experiment and pump it down and make a hard vacuum to work with the spectrum. Longer than 2,000 angstroms, the laboratory was awfully thin. They could just work with it. So this is an arbitrary convention that is not a law in atomic physics, but it's a strong recommendation, and Cloudy follows it. Cloudy wants to speak the lingua franca. This is changing. SDSS has always used vacuum for all wavelengths because their one telescope on the ground can look anywhere in the universe at low redshift, high redshift. JWST is even worse. It works at low redshift in a galaxy, and it also works at redshift 10. And so a given telescope will be looking at, in its rest frame, its laboratory frame, a particular wavelength, but it will be seeing transitions of a broad range of wavelengths. So probably the future is to use vacuum wavelengths for everything. Cloudy follows the tradition in atomic spectroscopy, but we include a command print line vacuum. So if you include that in the input deck, all of the wavelengths that Cloudy reports will be vacuum wavelengths, not air and vacuum. This is probably the future of astronomy, but it creates some very big puzzles right now. So here's some examples. This is the Lyman alpha line. That's unambiguous because it's a very short wavelength, so it's always reported in vacuum. Here are some very familiar lines. The strongest line frequently in the optical spectrum is O35007, and that's what I memorized from my youth. And in vacuum is 5008. Line blends are the last of the complications. This is a quasar spectrum, and it shows a number of strong spectral features, and almost every single one of them is a multiplet of lines and not a single line. So that what that means is there are two or more lines. In some cases, they're very close to each other. And if if the telescope does not have great resolution, or if there's internal Doppler broadening, the multiple lines will appear as one single line that's referred to as a blend. It's a blend of several lines. Three of the most famous blends you work with in AGN, the 03 to 3727 line, is the two lines very close to one another. Magnesium 2, 2798, carbon 4, 1549. So these are pairs of lines that are very close to one another, and it's very unusual to see them resolved as individual lines. So in the cloudy spectrum, which you see, this is the line out here longward of H alpha. Sulfur 2 is a very famous density diagnostic. At high resolution, you'll see one line at 6716, another at 6730. At low resolution, you just see a single line, a blend at 6720. So this is the output in the same units. This is the linear intensity. So you'll see that the blend is the sum of these two. This is a convenience. So if you've measured sulfur 2 6720, the blend relative to H alpha, you can just extract the blend and H alpha and study that intensity. Otherwise, you'd have to script up, plucking out each of the sulfur 2 lines and then adding together after the fact. The blends are defined in blends.ini. You can change the contents of this file, and Cloudy will use it without complaint. You can define new blends. And so this is a very common facility that makes it possible to work with observations and the limitations that some observations have. The last thing here is the units of these last two columns in the main output. So this third to last is what we call the absolute intensity. It's either the intensity of a line, which is this case what it is. So this is number of ergs per square centimeter per second, log. It reports it as a log. In the previous case, we saw it was luminosity of the line. We'll come back and talk about intensity luminosity cases in a later video. So stick a pin in it, we'll come back. This is the linear intensity. So here, 50703 is 23 times stronger than H beta. So this is probably a planetary nebula. So the default normalization line is H beta, but you can change it to anything else with a normalize command that's here in Hazy. So that's how you work with lines. It's a bit of a nuisance. We've inherited a lot of luggage from the 19th century and the mistakes they made back then. But once you get over it and work with these output report files, you can pluck out lines and then start doing some very, very interesting physics with Cloudy. We'll come back to that in future videos. Thank you.